Well, happy Monday to you. Hope you guys had a great weekend and are ready to start a new week and finish up chapter 10. We're going to finish up with polar functions. So last week we spent 2 days each looking at parametric functions and then vector representations. And now we're going to finish off with polar functions. So make sure your calculator's in radian mode as we move forward to polar, and that it's set to polar mode also. So we'll talk about the conversion between rectangular Cartesian coordinates and polar coordinates, and going back and forth, and then how to find the slope of a curve for polar functions. So we'll focus on the establishment of polar and the derivatives of polar today. And then tomorrow we'll work on the integrals with polar and how those are applied. So just a reminder, a rectangular coordinate, the Cartesian plane, is defined as x and y, the horizontal and vertical. Polar is defined differently. We define a point by its radius and its theta relative to the zero axis. So if you want to look for a polar coordinate pi half, 4 comma pi halves, what would be the rectangular coordinates for that? So just a visual of that, the angle would be pi halves, so that's going to get us all the way through the first quadrant, and then the radius length of 4, so that just puts us here at 4. And so in Cartesian coordinates, just visually, we can tell that that is 0, 4. So going from polar to rectangular is usually not too hard. You can do right triangle trig too to convert those. Okay, go in the other direction. Picture where the rectangular coordinates -3, 3 are. So that's going to put us into quadrant 2. Okay, we're going to express the radius that way as the length of that hypotenuse. So just an imaginary right triangle there. So the r would be 3 rad 2. And then the theta one expression of that would be 3/4 pi. That gets me into quadrant 2. So we could express this as 3 rad 2 and 3/4 pi. But you can express polar coordinates differently. I mean, that puts you into quadrant 2, but another way to get put into quadrant 2 would be to pick a different theta. So if I picked, say, theta being equal to 7 pi/4. Now normally a radius then would take me, into quadrant 4. But we can also run radiuses backwards. We can reflect them backwards. And so we could say, if we're going to 7/4 pi, rather than going forward into quadrant 4, we're going to go backward, -3 rad 2. And that still puts me back at that same position. So you can manipulate your theta and then manipulate your radius to still end up where you want to go. Sometimes it's to an advantage to use a different theta or a negative radius. The quickest way to go back and forth between rectangular and polar coordinates is to use the right triangle trig definitions. So if r is the hypotenuse, then we always define x as being r times cos theta, and y as being r times sine of theta. You can set those up in a right triangle trig. If r is always this and x and y, and this is theta, then those relationships are pretty easy to come up with. But that also helps us when we substitute going from polar to Cartesian ahead of time. So if we want to convert this into rectangular coordinates, a quick way to do that is to use that r cos theta. So r is 16, and then the cos of 5 pi sixths. So 16 times negative rad 3 over 2. So negative 8 rad 3. And then the y being our sine theta. So 16 sine 5 pi sixths, or 16 times half, so 8. And so the conversion then is negative 8 rad 3, negative 8, rad 3, comma, 8. And that would be in the same position. It would be in quadrant 2, just like 16 5 pi 6. Now you can create all different beautiful polar curves by setting up r in different ways. So if you did y equals on your calculator in polar mode, it would look like r equals. And anything, the most basic polar graph is going to be a circle. So if the radius is constant, we get a circle centered on the origin. If r is defined as a sine theta, you'll get a circle centered on the y-axis, and a cos theta would be centered on the x-axis. You're not going to have to memorize these. I just wanted you to see them for an example. You'll pretty much always have your calculator to graph these for you. It gets really pretty when you start doing things by multiplying theta by a constant, by n, and then you create what are called petals, and then these are called rose curves. So you can have different rose curves depending on if it's odd or even, depending on if you're developing it from sine or cosine. The symmetry changes. So again, you don't have to memorize this or know this. You'll always be able to graph it with your graphing calculator. Just wanted you to know the vocabulary. Limacons or limaçon, it's French. Okay, it's if you pronounce it, I think if I'm getting it correctly, it's a son instead of a limacon, or a shon almost with a sh if you study French. So these look like lima beans to me. They've got sometimes a little circle on the inside. Sometimes it's that circle's not fully developed. It's more of a cusp. Sometimes it's just a little indentation. And then other times, like you can barely tell that there's an indentation here. It's not a perfect circle, but it's a little bit out of shape. Again, these are just created by different combinations of adding and subtracting constants to sine and cosine. Lemniscates are when you start squaring things. Again, you don't have to memorize these, just know that they do exist. The spiral of Archimedes is fun. If you just want to try creating that, just do a plain old r equals theta on your calculator, and then set that little y equals with the little ball curve, the little ball with the tail, and watch it create this spiral. That is just basically saying that the radius is going to grow and get larger and larger as the theta grows and gets larger. Some of the identities, okay, we've already talked about these two. X equals r cos theta, y equals r sine theta. Those two lead to this one, that r squared equals x squared plus y squared. That's the Pythagorean identity for polar coordinates. And then that tangent would be y over x. So, of course, that should not be a surprise. You'll have r sine theta over r cos theta. The r is reduced, sine over cosine, we've got tangent. So these identities, these conversions, are going to be necessary when you want to convert so that you can take a derivative. So there are some times where taking a polar and putting into Cartesian form before you take the derivative is way easier. There are other times where you can take the derivative directly in polar form. So we'll do some of each. So here, for example, convert and find its slope. So I'm going to start with the fact that 5 times the secant of theta is the same thing as, 5 over the cosine of theta. So just using that identity and do a little cross multiplying. And so we get r times the cosine of theta equals 5. Okay, well, r times the cosine of theta is a identity, and that's equal to x. So x is 5. So the Cartesian equivalent for this is the vertical line x equals 5. And if you know that, okay, we have this vertical line here at 5. The slope of this then is undefined because it's a vertical in nature. So I don't have to do any calculus, I don't have to do any derivatives because I converted to Cartesian and I recognized what kind of an equation that was. So sometimes it's easier to convert into its Cartesian equivalent. Now the same will be true here again. I'm going to cross multiply, drop a 1. So that's going to give me 2r sine theta plus r cos theta equals 3. R sine theta is the equivalent of y, so this would be 2y plus, and then r cos theta is x. So this is the equivalent of y equals negative 1/2 x plus 3/2. And so the slope is negative 1/2. So this is just a linear function, and so it's easy to tell what the slope is. Other times that conversion does not help. So we would need to convert differently in order to figure out the slope of an equation. Okay, there's no cross multiplying here. I don't have a denominator, so I got to think of something else. So I would like there to be an r right there, because r sine theta is something that I can work with. So how can I get an r there legally? Well, the only way I can insert an r into that multiplication is to put an r on the other side as well. So I'm going to multiply both sides of my equation by r. That's going to give me r squared equals 4r sine theta. And what that's done is it has created two identities that I can substitute for. So r sine theta right here is y, and r squared can get replaced with x squared plus y squared. So now I have a completely Cartesian equation, and I can find the implicit derivative here. So 2x plus 2y dy dx equals 4 dy dx. And I can divide the whole problem by 2 and then solve for dy dx so that I can find an expression for the slope. So dy dx would be y minus 2 if I gather them on the same side, and negative x if I kick the negative x to the other side. So the slope of this polar graph can be expressed in Cartesian form, negative x over y minus 2. So maybe just an easier way to express it now that you have your Cartesian equivalent. All right, other times it is easier to find the derivative a little bit different way. So let me show you another way that we can find the derivative. I can find it using components. So I can say, all right, well, if in this rows, r is defined as 2 sine 3 theta. And so we've got x is always defined as r cos theta. And if r is this, then x is 2 sine 3 theta times cos theta. And y is always r sine theta. So that would be 2 sine 3 theta times sine theta. So then if I want to find the derivative, find the slope, I can find dy over dx. So I can do it with components. I can do the vertical over the horizontal. So 2 sine 3 theta times sine theta needs the product rule. So I'll have 2 sine 3 theta cos theta plus 2 sine theta cos 3 theta times 3. That's the derivative of y with respect to theta. And then we'll find the derivative of the component x. So that'll give me 2 sine 3 theta times negative sine theta plus 2 cos theta times cos 3 theta times 3. And then we want to plug in pi sixths. We could reduce a 2 from everything, I guess, first. So all of these have the coefficient 2. Okay, then we can plug in pi sixths. So sine of 3 times pi sixths would be the sine of pi halves. And then the cosine of pi sixths. Plus the sine of pi sixths and the cosine of pi halves times 3. Now the cosine of pi halves is 0, so that'll negate that whole second half of the problem. And then we've got the sine of 3 theta, so the sine of pi halves, times the negative sine of pi sixths, plus the cosine of pi sixths, times the cosine of pi halves again, times 3. So again, that'll be gone. So to simplify, we'll have 1 times rad 3 over 2 over 1 times negative 1/2. So negative rad 3. So there's just 2 different ways you can do it. You can either switch it to Cartesian and apply a Cartesian rule, or you can do it in component form and then find the derivative that way. Okay, so we'll come back together on Tuesday and we'll talk about how to do integrals related to polar graphs so that we can find the area, and then that'll finish up chapter 10. All right, I hope you guys had a great weekend and a good start to your week, and I'm looking forward to seeing you on Tuesday.